Hi everyone. Remember that your data type determines the statistical methods that are appropriate for analyzing your data set. So, for example, if you were to have a continuous response variable and a continuous predictor, regression and correlation would be appropriate. On the other hand, combining a continuous response and a categorical predictor, ANOVAs and t-tests would be appropriate. And of course, if you have a continuous response variable, but both continuous and categorical predictors, well, then you can combine those into a linear model. In another scenario where you have a categorical response and a continuous predictor, then logistic regression will be most appropriate. And remember that categorical predictors are also possible within logistic regression. Finally, and the focus of today, when we have a categorical predictor and a categorical response, then chi-squared tests are appropriate. This is especially true when one's counting the number of observations in different categories. So, in this recording, we are going to be thinking about contingency tables and chi-squared analyses and how they allow us to analyze categorical data. So first, let's just define what categorical data looks like. Essentially, you are generating categorical data when your measurement scale, in other words, how you're recording your data, consists just of one set of categories. Okay? So think of shirt sizes, small, medium, large. Right? That is the scale on which you're recording your data, and it only comprises a set of categories. And importantly, each object or each observation can only fall into one category. You can't have a t-shirt that is both small and large. One of the questions that you might ask during this presentation that I want to tackle quickly now is, can continuous data also be analyzed using the same methods as for categorical data? The simple answer is yes, it can, but that requires converting continuous data to categorical data. And when we do that, we lose information, which means in the end that we have lower statistical power. So yes, you can analyze continuous data, for example, with a chi-squared analysis, but you won't because you lose too much statistical power. Let's think of an example question that we can use as we move through thinking about chi-squared tests. And I'd like to suggest that we think about this question of whether trees are more common or more frequent or are more likely to occur on the northern or the southern aspects of the Rocky Ridges in Gauteng. So you could think, for example, of the Magaliesberg, which runs through Pretoria North. And these two images are from the Magaliesberg, and you can see in them the south slope looks like it has far fewer trees than the north slope. And this is an observation that you could make on other ridges around Gauteng. So this then is a nice example where both the response and the predictor are categorical. The response is the presence or absence of trees, and the predictor is aspect, in this case north or south. So fortunately, we have data to answer this question that's been collected by the BOT 358 class in previous years. Quadrats of 4x4 meters were surveyed on the northern and southern aspects of the Magaliesberg, and from that we can extract whether trees were present or not. We're going to use data from 2017 to 2019. After excluding quadrats with aspects that aren't nicely north or south, we're left with a sample size of 107 quadrats. That's a nice big sample size. You can see how the data looks here. Again, you can see that aspect clearly just has two categories, north and south, and trees present, either a yes or a no. So again, two categories. Our null hypothesis here would be that there's no relationship between aspect and the presence of trees. There are various other ways we could say that. For example, we could say that the proportion of quadrats that contain trees is similar in the north and south aspect. Okay, we've got our raw data here already. And I think an important question to ask is, how do we summarize this data? And I'd recommend that you take a minute here and pause and think how you would summarize this data. So, the simplest way to represent this type of data is in a contingency table. This table here already summarizes those 107 quadrats into just a matrix of 2 rows by 2 columns. We'd call this a 2 by 2 contingency table, and the 2 comes from the fact there are just 2 categories for aspect and just 2 categories for tree occurrence. Already we can see a very nice summary here. We can see that there are, for example, more trees present on the north than trees are absent from quadrants in the north. Okay, but obviously we need to analyze this formally to determine whether this result is maybe just by chance, or whether it reflects, or how likely it is to reflect a real pattern. One of the first things that we can do is we can add marginal totals in red and a grand total in blue. You can see the grand total, 107, that is our total sample size. And by looking at the marginal totals, for example, you can see that there's a very similar number of quadrats surveyed on the north and the southern aspects. Now, contingency tables reflect our observed data. How many quadrats had trees versus didn't have trees on the north and the southern aspects. But if we want to determine whether this supports our hypothesis, what we need to do is we need to know what the expected number of observations in each category would be if the null hypothesis was true. In other words, if there was no association. So how do we go about determining what the expected observations would be when there is no relationship or no association between the 2 variables we're examining? This is a simple process, but it's also something that statistical software will do for you. However, I want to just walk you through it so that you can understand what's happening in the statistics. We're going to switch to a different example temporarily now, and we'll come back to the tree presence on the different aspects later. So this slide represents data collected from 952 people, and it tells us what the number of men and women are that have blue eyes or do not have blue eyes. Okay, so this again is a 2 by 2 contingency table because there are 2 options for this category and 2 options for this category. So how do we go about calculating the expected values? Well, again, let's recap. Our null hypothesis is that there's no relationship between sex and eye color, and we could word that formally as the proportion of blue-eyed people is the same for men and women. You can see here in our data set we have 88 blue-eyed men and 70 blue-eyed women, giving us a total of 158 blue-eyed people out of the grand total of 952 surveyed people. That then means that the proportion of blue-eyed people is 16.6% as observed in our data. Now, if there's no relationship between sex and eye color, that means we'd expect 16% of all of the men, that number there, 16% of that number, to be blue-eyed men, and 16% of that number to be blue-eyed women. That then allows us to put our expected observations, our expected values, underneath our observed. Okay. And it's actually really easy to work out those expected values. It is simply the row for every cell. Again, let's come back to this cell. The expected value is the row total multiplied by the column total divided by the grand total. So we can easily work this out, the number of blue-eyed men and women and the number of not blue-eyed men and women. And that then gives us our expected values versus our observed. And what you can see here, for every category, there's a difference between the number observed and the number expected. And that difference is the basis for the statistical test. So that data is used to calculate the chi-squared test statistic. You can see here the chi-squared, so chi is just looks just like an x. The chi-squared test statistic is determined as the difference between observed and expected squared divided by the expected all added up. So your statistical software will calculate that number for you and then will give you a p-value, testing whether the difference between observed and expected is bigger than expected by chance. Okay, in this case we can see we get a p-value that is larger than the 5% threshold, and we can therefore not reject the null hypothesis. In other words, we don't have strong evidence that there is an association between eye color and gender. Okay, in other words, the difference between the observed and expected values is not large enough that we can conclude there is a relationship between eye color and gender. Let's look at another example. So here we've got a 3x3 contingency table. You can see for plant reproductive strategy, we've got hermaphroditic, monoecious, dioecious. And for plant growth form, we've got herb, shrub, and tree. This is a data set that was pulled together specifically to address an idea that several researchers have had, including Charles Darwin, who might have been one of the first to propose it. And that's the idea that plants benefit more from cross-pollination than from being self-fertilized. So one would expect that monoecious and even more dioecious would be dominant strategies, that they would be more common than expected by chance. Let's have a look at this data set and let's calculate the expected values. So here we have for every category 3 values. The first is the observed. In other words, there are 379 herb species that show a hermaphroditic reproductive strategy. In other words, they've got perfect flowers. Below that we have the expected value. In other words, if there was no relationship between growth form and life history strategy, that is how many observations there would be. And then we've also got a third value, right? This is a standardized residual, and really all that it's telling us is the difference between observed and expected. And where the value is positive, it means that the observed is bigger than expected. And where it is negative, it means the expected is bigger than the observed. You can see here we have our marginal totals also, and our grand total. And then here we've got our chi-squared statistic, our degrees of freedom, and our p-value. Now, of course, let's update that, make it correct. We never expect, we don't report p-values of 0. A p-value of 0 doesn't make sense. Instead, we just say the p-value is very small. How do we interpret this p-value? Well, it's telling us again there's a significant effect here. And indeed, it's saying that there's a significant relationship or association between reproductive strategy and growth form. Logical next question, though, would be which growth form is showing disproportionate representation of which reproductive strategy? Okay, well, let's look for this at our residuals, and we'll first identify all of the positive residuals. Okay, this then shows us that for herbs, they are more likely to have a hermaphroditic reproductive strategy. Shrubs are more likely to have a dioecious reproductive strategy, and trees are more likely to have a monoecious or dioecious reproductive strategy than expected by chance, or if you want to say it differently, as expected when there's no relationship between reproductive strategy and growth form. So we could conclude here, especially since we already know that the difference is significant, that larger plants like shrubs and trees are more likely to be dioecious, and smaller plants are more likely to be hermaphroditic. If we want to be exact, though, we'd also say larger plant species and smaller plant species, because remember, that value there, that count, is the number of species. One issue here that I want you to just note quickly is that we have a lack of independence. Many of the herbs that were surveyed here probably fall within the same genus or the same species, the same family. Equally, many of the trees surveyed here are likely within the same genus or the same family. And since there is this phylogenetic relatedness, since we know that some of the species in the herb group and in the tree group are closely related to each other, we can't consider them truly independent. Okay, so the chi-square test is pretty easy to do, gives a clear answer. Can we use it always? Well, it's a little bit tricky here. Yes, a chi-square test can be applied to pretty much any data set where you've got two categorical predictors and you have a count of the number of observations that fall into each category. However, when the sample size that you're working with is small, then the results of a chi-squared analysis are not necessarily robust. Okay? So there are lots of different rules of thumb about how many observations you need, but the simplest ones could be summarized as saying you need to have roughly a value of 5 in each of your categories for expected values. There are other less strict rules. For example, it's been suggested that as long as every expected value is greater than 1, and most of them are greater than 5, then your results can still be trusted. It's worth noting that for a 2x2 contingency table, the general rule is that all of the expected values should be greater than 10. Okay? However, if you have a data set that is so small that you don't have that minimum number of observations within a category when you're looking at the expected values, there is the option to use Yates's continuity correction. And this is actually automatically applied when you run your analysis in R. And it just makes your chi-squared analysis a little bit more robust to small sample sizes. The other option here is if your sample size is very small, then you can use a Fischers exact test. And essentially, this is a version of the chi-squared test that's appropriate when you've got very low numbers of observations. However, for your analyses, I think the chi-squared test is going to work well. Let's return back to the Rocky Ridges and the Michalisburg Ridge in particular and see what we can learn from our chi-squared analysis. So we know our raw data can be summarized into a contingency table. We know that we can run a chi-squared test, and we can see that we have a highly significant value here, p value much smaller than 5%, telling us that yes, there is a significant association between the presence and absence of trees and the northern and southern aspects. Then to find out where that difference lies, we can look at the expected values and the residuals, and by comparing expected to observed, or by looking at the residuals, we can see two things. We are more likely to find trees on the northern aspect than expected by chance, and less likely to find trees present on the southern aspect than expected by chance. Therefore, this analysis suggests that our observations of there being less trees on the southern, or trees being less frequent on the southern aspect, really does reflect a true biological pattern. If you're going to be running chi-squared analyses, remember that there is an R code file and another example available. You can find that associated with this presentation. And then good luck with your analyses.